Okay, so today, guys, we are going to work on Ensemble Models. We're going to look at Ensemble Models. I'm going to share my screen. Okay, can you see my screen, guys?
Yes, sir.
Okay, good. Okay, so this week, basically, we want to look at the implementation of Ensemble model for classification and regression problems. So these are the models we want to use. We want to use bagging, we want to use random forest, and we want to look at boosting. These are types of Ensemble models. The question now is, what are Ensemble models? What are they? You know, in the past few weeks, we have looked at a number of machine learning models. We look at multiple linear regression, starting with simple linear regression, multiple linear regression. We moved to support vector machine. I think we did random forest. No, decision tree rather. We look at decision tree last week, and then we've discussed KNN, K nearest neighbor, for classification and for regressions, right? So these are just single machine learning model. They are just single estimator. Ensemble models come with the need to combine the capacity or the strength of different models. You know, I have a machine learning model. I have a machine learning model. Can I actually have the models combined to have a stronger and better model for my classification or for my regression? This is the concept behind Ensemble model. So again, Ensemble model is just an aggregation of more than one model in order to improve the performance of your model. So that is invariably informing us that in Ensemble model, we will have something called a base estimator. I'm actually trying to give you the intuition behind Ensemble model, because understanding the need or the purpose of Ensemble model is very vital to understand what we are doing in this lab. So, okay, what was I saying? I said there's different types of Ensemble models. So we have we have bagging, we have random forest, we have boosting. You see, generally, Ensemble models can be classified into model that do averaging of the different models, and one that do boosting. So this one is an averaging of Ensemble models. This is a boosting. What's the difference? We are going to look at it. So basically, let me give you an overview of what we want to do in this class, and then maybe we are not going to go over the code, and then I'm going to now maybe explain more what each of the machine learning models are doing. Okay, so first we want to use a bagging. We want to use bagging for classification problem, and then we're going to be working on titanic data set, right? Bagging for classification problem using titanic data set. So that means we want to use bagging to predict the survival of a passenger in this titanic something. So the next one is we want to use random forest for regression. So in this case, we are working with ETA's data set. So basically what we want to do is we want to look at how well random forest can predict the salary of a baseball player based on the I think the its and the years, right? We work with these two. We have been working with this data set in the past, and then more importantly, last week we used this same data set, or we solved this same problem using decision tree, right? This is lab 8, where we use decision tree, right? For this, where is the section? For ITER and the Titanic. So we want to look at it. How well can we improve the performance of our model from the last lab? How can we be better in the production and the classification? So we want to consider Ensemble model now. Okay. So then the last one is for the same Titanic data set in the first example, we want to use boosting, right? Boosting is, like I told you, there are two methods to assemble models. The first is to average different individual models. That one is just averaging. So you have 20 models, you have 20, all the models divided by 20, right? Then the next one is boosting. This is boosting. So this boosting, we are going to see which of these techniques have averaging or boosting, which of them is better. Random forest tool is averaging approach. It average many decision trees. Anyways, let's start with the first. Okay. Now, begin with, as usual, importing the necessary packages for our machine learning work. So we import NumPy as NP. We import pandas. This is the model assessment function metrics. This is for the splitting of our data set, the twin test splits. And this is for our base estimator, the decision tree classifier. Remember, we import the same packages in the last lab when we want to use decision trees, right? So, but then here, but the difference between the usage of decision tree classifier or decision tree generally in this lab and last week lab is that for last week, it is our main model. Decision tree was our main model, right, last week. Here, we are going to see that decision tree is not our main model, but it is our base estimator. It's our base model, right? Okay. And then we import standard scalar, right, for scaling or for transforming our data set. And then we import the bargain classifier. So this is our main model now. This bargain is our main model, but decision tree is the base model for this bargain classifier. So this is the idea behind a Ensemble model. You have the main model you want to use, and you have the base model, which are to be average or to be boosted. So now what we are doing here is we want to average many decision trees to get a bargain model. Okay, so we run this. Let me see if I have to clear. I need to clear outputs. So let me clear our outputs. Okay. So now let's start with this. I import my packages. That's taking some time. Okay, so I want to read my file, and then I need to load the document. Yeah, I think it's Titanic here. Okay, so I have it there. So then I can now run this cell. Okay, so the Titanic data set, we can check if there's missing values. You know, we did all of this in the last lab, so I will just quickly run up through them. So there is no missing value because it has been, you can look at it. What does it look like? We have this, right? And then, you know what this line of code is doing? Is basically to encode the sex column. in order to change it to numeric values. Male is going to be 0 and female is going to be 1. So that's why we use np.where condition. So we store that in m6 column, and then we can now look at the data frame again and see that we have the m6 column. Okay, so basically what we are doing now is just data preprocessing. We are preprocessing our data. Is a very important step in machine learning. So we want to define our inputs and our targets. The input are the predictor or the independent variables, and the target is the y, or the dependent variable, or the predictant, what we want to predict eventually. So we just use this called the column, and then we want to split, right? We use twin test splits, right? And then we pass our data set x and y. So that means for x we are going to have x twin and x test, and for y we'll have y twin and y test. And what was the splitting size? That will be text size of 0.5. That means 50% for training and 50% for testing. Okay, so we pass that. Then the next important thing in data preprocessing is transformation, right? And I told you the importance of transforming your data, right? Which is you want your data to be in the same scale or in the same range, because this is important for some machine learning models, especially the ones that use distance in their parameter this selection, like k-nearest neighbor, like linear regression, like support vector machines. You know, it's important to scale your data. It affects your model performance. Okay, so here we use standard scalar, right? We use standard scalar, and I think I explained the concept or the intuition behind the use of standard scalar in one of the past classes. Just to recall, standard scalar is used to transform your data set into a range of such that the mean of the data set is 0 and the standard deviation is 1. So your data set is going to be transformed generally to have a mean of 0 and standard deviation of 1. So these are data sets. Before you can see, look at it, age 22, 19, and all of these, Now, to do that, we just call the standard scalar method. Then we now fit to make it learn. We fit it on the data set, and eventually we now transform the data with the standard scalar. So we just call it sc.fit_transform. So we transform the x twin. We also transform the s text. Okay. So you can look at x twin or something. So you can see it has changed. You have 0 minus something. So you can see this is like we find the mean of each of this column is going to be 0, and the standard deviation is going to be 1. Okay, that's it. You can use another transformation method called normalization. Normalization basically scales your data between 0 and 1. I mean, by default, but you can change the range of values, maybe to -1 or 1. But by default, it scales your data between 0 and 1, such that the minimum value in your data set is going to be 0 and the max is going to be 1, right? The formula for, to use that, you can use this method, min max scalar, in scikit-learn. There's also min max scalar. So instead of when we wanted to import the standard scalar, we use from sklearn.preprocessing import standard scalar. But here you can use from sklearn.preprocessing can use standard scalar, min max scalar. Yeah, you can see min max scalar. So this is it. So min max scalar. You can just import here mean mass scalar. So it's still the same thing it's doing as standard scalar, but in this case now, it is now transforming your data between 0 and 1. The standard scalar transform your data just to have a mean of 0, but here between 0 and 1. The intuition is if you have xi, then it is going to use this formula x for the transformation xi minus mean x mean divided by x max minus x mean. So basically, it's just normalizing your data. Well, you can read more about standard about mean mass scalar. So let's proceed. Now to the main task of building a bargain classifier, right, for classifying the survival of a passenger in the Titanic dataset. Now, basically what we want to do, let me just give you an intuition. What we want to do is we want to initiate our model. Let's say BGC, bargain classifier model, is just called the estimator bargain classifier. Now, look at what happened. When you call the estimator, if you look at the parameter, before start, let's even look at the description here. A bargain classifier is an ensemble meta estimator that fits base classifier each on random subsets of the original data set and then aggregate their predictions to form a final prediction. Let me explain that to you with paint in a very quick. I don't have writing pad, but I'm going to try to make use of my mouse, but it's not going to be best. Okay, but let's see. Bargain now. Bargain. Let's assume we have this length of data set. In our case now, it is where's my browser? In our case, it is Titanic data set, and the length is 714 from index 0 to index 713. Okay. This is the total length 713. Now, let me go back to my browser and where's my plugin? Look at it. A bargain classifier is an ensemble meta estimator that fits. Let me just copy this out. Let me just copy this out so that I can now paste it somewhere here. Okay, now look at it. A bargain classifier is an ensemble meta estimator that fits base classifiers, each on random subset of the original data set. Let's say for this data set, we have subsets, random subset here. Let's say this is the first random subset. This is just, subset, not total. So this is the first random, R1. Let's say another random now is, something like random, just can go anyhow. This is R2. And then another random can be from here to here. We have R3. Let's say we now have another one now, R4. These are random subset. We have 4 random subset now. Let's assume we have 50 random, or let's say 5 random subsets. Okay. What bargain want to do is that it want to fit. Let's go back to it so that I can use the it fits base classifiers. Now, what are base classifiers? They are like the decision trees. They are like the k nearest neighbor. They are like the support vector machine and all of that. So it fits base classifier on random subset of the original data set. Now, from this thing that I showed you, we have 5 random subsets now. So that means it's going to fit. If you want to use decision tree now, it's going to fit decision tree on these 5 random subsets of the data set. And then what happens after that? And then aggregate their individual predictions, right? Either by voting or by averaging to form a final prediction. You see? So what it means is that, let's say for this first subset, for R1, we build a model decision tree 1, right? And then we continue like that for up to R5, random subset 5, to build a model decision tree 5. Okay, now after building the model, we can now use the model, each of the model 1, 2, 3, 4, 5, decision tree 1 to 5. We can now use each of these model for prediction. Let's say we want to predict now a new data set x1, age something, and then p class. These are the predictors. So when we pass s1 into dt1, we are going to have y1. Let's say for y1, which is the prediction from dt1, we have that for this x, the person survived, it predict survive, and then the same x is passed to dt2, right, which is the model based on the random subset 2. Then we are going to have y2, which is the prediction of dt2 for the same s to be, let's say, 1. So they predicted the same thing, or they classified the same, they put on the same classes. Then for dt3, let's say we have y3 to be 0. Then for dt4, we have y3 to be 1. Then for dt5, we have y3 to be like maybe 0 or 1 or 1. So now the point is, the final classification is going to be an average of all these things. So which of them has the best something? So here now, 1 is 3 models. 3 models predicted 1, but 2 models predicted 0. So we can say that here now, 1 is the best prediction. So the best prediction is 1. So this is the idea behind the use of bagging. So bagging is this is basically how bagging works. So now that you understand, so you should know that when we want to initiate our bagging classifier, you're going to have something like the base estimator, right? You see, the first thing is the base estimator, which in most cases is usually the decision tree for bagging. If we don't pass, we can pass the value, but if we don't put the value, it's going to consider the decision tree as the base estimator. Then the next one is the number of Excimators. In the example that I showed you, the number of Excimator is 5, because we use 5 samples and then we fit on 5 models. So you can set the number of Excimator to be 10 or to be any number you feel is going to work well. Then the other ones, you can leave it by default or you can change it. One important thing that you want to consider also here is the bootstrap. What is bootstrap? Bootstrap is used to control the solving or the sampling of your data. So if you set bootstrap to be equals to true, that means it's going to sample with replacement. If you read this thing, bootstrap, when samples are drawn with replacements, so this is when it is true. Okay, so what does that mean? It means after our first sample here, R1, and we use R1 to build our first model, it's going to put the samples, R1 samples, back into the data set and then be able to do another random sampling. So that means R1 can still be some element or some data point in R1 can still be included in the next sampling of R2. Okay, so these are the what's it called? The parameters. Okay, so this is the conversion. So I'm just going to take you through this. So we want to build the bagging model now. We initiate our DTC to be the decision tree classifier, which is going to be the base estimator. Then we call our bag model. We initiate our bagging classifier. The base estimator is now this DTC. The number of estimator is 100. We set the bootstrap to be equals to true. You can read more about bagging classifier here. Then after we initiate it, we just do the normal machine learning steps. We fit our model on our data set. We now use our model to predict. Then we can find the score for our model, bag_model.score. So we just pass S test and the Y test. Okay, let's look at that. Let's look at, we're going to run that. Okay, so you see we have 0.753. We just put this up. Let me put it down. Okay, so we have 0.753. So this is the performance of, that means 75% for the test set. It's has 75% accuracy. Okay, so this is the performance of our model. How well does this one perform compared to the last one? Let's see. In the last class, we used just a single decision tree. Where is it? Titanic. Yeah. We use just a simple decision tree here. And then we have, where is the performance? 0.71, right? We have 0.71. And, this gives 0.75. This is 0.71. Okay. Actually, this one performs better than this because this is now bagging. But then you can look at, well, the performance is not too much or too superior to the single use. Well, the point is there are still some parameters that you can change to improve the performance of your bagging. So we're going to look at that maybe later. Okay, so let's move to the next. Now the next, looking at the parameters is the next thing. So the next thing now is, here we can decide to use, let's say 5 this thing here. If we use 5, you see the performance is reduced 0.72. Whereas when we use 100, it is 0.75. Well, you might think that if we keep increasing the number of estimators, then the performance will keep on increasing. Well, that's not going to be true in most cases. So the point is, how do we know the best parameter to use? In fact, this is a very is usually the question in almost all machine learning problems. What is the best parameter and what is the best model? I have many models. I have support vector machine, I have the decision tree, I have this, I have that. What is the best model? And then I have different parameters for each of the models. What is the best parameter to use? So, this is where validation comes in. Model validation, right? And then I think one of the class we look at cross validation. But here, what we want to do basically is we want to use a very similar approach to cross validation. Here we are using validation curve to determine the best parameter for this number of estimators. Right? In other words, to determine the best or the number of decision trees to use in our bargain classifier model. Okay, so to do that, we want to plot the performance of each of the parameters. Then we import matplotlib. Then here we are going to use validation curve inside the model selection, right? So now we want to test for some set of values as the n estimators here. We want to test between 1 and 250, but we want to sample at interval of 5. That means 1, 6, 11, up to 250. Okay, so that's why we created NP arrange, start from 1 to 250, step at 5. Okay, let's look at what that looks like. So here we have the parameters that we want to check, right? So basically what we are doing here again is we want to find out among this range of values, which is best for my bargain to use as a parameter for my bargain model, right? Which is best to use as the value of n estimator parameter of my bargain model, right? How many values do we have here? Let me see. Can I use size? That size. So we have 50. We have actually 50. So that means we want to test for 50 parameters. I mean, not 50 parameters, 50 values. We want to test for 50 values. Okay. Now I want you guys I want to explain this line of code here. To test, we want to create a validation curve. Validation curve. Now, the validation curve is asking, these are the parameters. What is the estimator? What the estimator is the bargain classifier, right? Is a bargain classifier? No, I think we define it as B. Let me see. Bargain classifier. Okay, bargain classifier. Yeah. So the estimator is bargain classifier. We just call that. And our X is X train. Is it X train? I just pass X or something, Y train. Now, the parameter name, what is the parameter name? The parameter name, which is the parameter we want to test, is the, what's the parameter name? N estimator, I think. N estimator. The number of estimators. So I will just have to put this in string. N estimator. And then now, what are the parameter range? What are the values that I want to check? I want to check between 1 to 250. I define it already here as parameter range. So I'll just copy this here, put it here, parameter range. And then another thing you want to put is the CV. The CV is like the cross validation. Remember, cross validation is used for, training and validating your data. I mean your model. So what it does is that it's going to put your model divided into different samples. By default, it's usually 5. So you're going to divide your data set into 5 samples. Then it's going to go across the 5 samples and put it in different. I mean, one of the sample in testing, then the remaining 4 sample in training for training. Then it moves again and do the second sample for testing and the remaining for what's it called, for training. So in essence, it is doing k minus 1 for training and then leave the remaining 1 for testing across the 5 or the number of steps. So I'll just say CV. My CV is 5. And what is my scoring? The scoring is, you can say, accuracy or something. So if you leave it, it's by default, it's going to take the default something. So this is basically what we are doing here. I just break it down for you. So that's what they are doing here. So the validation curve, the base estimator is this, the X train, Y train for the X. The parameter name is number of estimator, which is the parameter we want to find the best value for. Then the range is param range, which is days, right? These values. I don't need to do that. You have seen it before. So the CV is 5, and the accuracy and the end job is -1. Okay. Now, what is the return from this thing? It's important to understand the return. You see, the return for this, because we are going to plot it now, and it's important for you to understand it. The return from this is for each sample, like for each value in the parameter range, is going to use bagging classifier, I mean the base estimator, on the data set using each of these samples, right? That means you have 50 what's it called, trials, basically, because we have the number of parameters here is 50. So you have 50 trials, basically, such that the first one, we can call it 1, will be fitted, and then you have the performance. Now, another thing is, it's not going to assess it, the train scores and the test scores. So basically, you have 50, I just want to break it down, 50 train scores and 50 test scores, right? So you can see train score 1, test score 1, right? Then you have this up to 50, right? Train score 50, test score 50. Okay, and for the 1, you know, this is 1. For the 50, is going to be 246 as the number of parameters. Okay, now another thing that you should know is that because we are using cross validation of 5, right? That means we are going to have 5 instances of this train score and test scores, right? Because, I mean, we are going to have 5 scores, basically. 5 scores for each of these. Anyways, this is just a breakdown of that. That's why we are having train scores, test scores. Train score is the collection of the train score. Test score is a collection of the test score. Okay. Now let's look at what train scores look like. Oh my, I didn't run this. This will take some time. I should have started running it when I was explaining. Validation curve. Okay. I'll just comment this out or delete it. Okay, so this is going to take some time. So basically, that's why the reason why it's taking some time is that it is doing for, you know, different parameters, right? And then at different cross validations. In fact, I've been doing something similar, which is grid search. I've been doing grid search on a particular data set since yesterday, and it is still not completed. So it can take long, but now for this one, it shouldn't take that long. I want to show you the one I'm doing. This is what I've been doing since yesterday for this model. and it is still not completed since about 8 p.m. yesterday. Why? Is the reason is because I'm using different models, different parameters, I'm combining them basically. So it might take like 2 days or a day to come up with the best with the result basically. Anyways, where's my okay? So now we have our twin scores and the test scores from our validation curve. So we can now check that. Okay, this looks somehow. So this is our array, twin scores dot shape. What do we have? What do you think is what do you think these values are? These are your twin scores for each of the parameter. I mean, for each of the parameter value. For the first parameter value of 1, you have your twin score for the 5 instances of the cross validation. This is for the first cross value of CV, second CV, third CV, fourth CV, and the fifth CV. And this is for the first parameter value. And this is for the second parameter value. This is for the third. And the last one is for the 50 parameter values. So by default, you expect that you should have shape of 50 by 5, 50 rows for the parameter value, and 5 for the different trials of the cross validation. So if I do this, I have 50 by 5, right? Okay. So what I want to do is, since the rows are the important something, right? 50 is 5 values. I mean 50 rows, the one for each of the parameter values. So I just want to find the mean across each of the rows. Find the mean across here. So I can now have 50 by just 1, which is going to be the mean of the 5 cross validation. So that's what I'm doing here. Twin mean equals to np.mean, and then find the standard deviation across all the 5 cross validation. So let's look at the twin mean. You can see this is now our twin mean now. It is now 50 rows of values, each one for the mean of the cross validations. You can see this one is for the mean of all of these, and the last one here is for the mean. This is its mean. Okay, so basically what we want to do is we want to find out which of these is the best or is the highest score, and then the one that has the highest score, we are now going to look at the parameter value that gave that highest score and then use it. But then remember, this is on the training. We also need to check for the test also. So we can find the marks here, but it's not necessary for now. So let's check for the test mean also. We have created the test mean and the test standard deviation. I'm just going to delete this. Twin scores dot shape. I think I've looked at this. Okay, now we want to plot. We want to plot each of these. Remember, we have 50 parameter values and we have 50 scores, 50 training scores and 50 sample scores, right? So we want to plot it. Plot the parameter values on the horizontal axis, and then plot the scores against plot the parameter values against the scores. That's what we are doing here. So that's why we call the matplotlib. Then we plot the parameter range, which is the parameter value, and the train mean scores. We label it this training score. We plot the parameter range and the test mean, label it the cross validation score. Then we want to fill the plot. We want to fill it to have the what's it called? The band for the minus and positive standard deviation. So this is the lower field range and this is the upper field range. Okay, so we label it. This is the title, this is the X label, this is the Y label, and then we now show. Okay, so this is what we have. You can see this is, if you look at this thing, this is our cross validation score, which is the score on the test. You can see this is how it goes from the n parameters of 1 to n parameters of 240 something. Okay, then this is the training, right? This is the training. So, and it's range between 0.7 to 1. 1 is the perfect score, but it range between 0.7. Now, what is the purpose or what is the benefit of this curve? The benefit of this curve is it will make us to decide or to be able to determine the parameter here that is best for our bargain classifier, because this is where the concept of bias and variance comes in. Bias and variance. Bias and variance, and basically what you call overfitting and underfitting, right? Overfitting and underfitting. This is where it comes in. You see, there are some models that they are going to perform. Some model will not perform well on the training and on the testing data sets. Meaning that, look at this one now. The training is low, and then the testing, the cross validation score is also low. So this one is called underfitting, meaning that your model is not learning from your data set. So it is giving a poor performance in the training and a poor performance on the testing. So this is called high bias. The bias is high. Okay, then another machine learning problem is your model is going to give high performance on the training, right? But on the testing, it's going to give low performance, right? If you look at somewhere around here, okay, I think here, you see that the training is low here actually. The testing validation is low, but you see the training is high here. The training score is high, almost 1, but here it has low something. So this is what is called overfitting. Your model is overfitting your data. Basically, it is just cross-working on your data. It is just fitting your training data, but then it's not learning actually. So it is going to perform well on the training data, but on the sample data, it's going to perform poor. So what we want to do, right, is to find the this problem is called bias variance dilemma, right? You have bias, you want to reduce the bias, and you want to reduce the variance. So basically, you want a model that performs well on the training and also performs well on the testing, right? Well, by default, it's almost impossible to have a model that performs well on the testing and then performs low on the training, right? It's almost impossible to have higher performance on testing than on training. So what we want to do is you want to get a model that performs well on training and on testing. So basically, we are looking at that point here. This is the use of this validation curve. We are looking at it. Which parameter gives me the best performance on the training and on the testing? And then you can see that, well, here you have high performance on the testing. At least the highest performance on the testing is here. You can see, but then it doesn't give us the highest performance on the training. So it's, for me, I can just go with something around this thing, something around here. So this one here, then I have a very good performance also for the training. So this is use of the validation curve. So from now, you can now pick your number of twists to be something around 55 or thereabouts, and use it in your classifier now, in your bargain classifier. So this is this is how you do ensemble bargain model. So I'm going to pause here and then ask if you are going to, if you have any questions for me before we move to the next one. Any question from you guys on bagging, classifier? Hello, can somebody talk?
So far, okay, sir. We need some time to digest the info.
Okay, good. Now let's continue. Let's move on. Okay, so the next thing is we want to use random forest. So this one is going to be quick because I took my time to go over the bagging. So it's just the same approach with bagging. Basically, random forest, as the name implies, is, you know, forest is made up of many trees, right? You cannot have a forest without trees. So the same thing, that's the intuition behind the name. So random forest is is an ensemble model of multiple decision trees, basically. So we want to use that. Remember, in the last lab, we used decision tree for this regression problem, eta data set, and then we obtain a score of where is the score? Where is the score? We have root mean square error of 530. Okay, for this. We have root mean square of 530. Okay, let's see what random forest we do. And remember, random forest is a combination of multiple regression trees. So it's the same, it's actually the same task, but we are now using different model, ensemble models basically now. So what I want to do now is I want to load my my data. I'm going to import it as dataset, upload. Okay. Yeah. So I have it. I can now read my data. Then check if there's missing values, and then you'll remember that we have missing values here. And what we did is we drop the NA values, and I told you, remember that it's not always the best to drop your NA values, because especially in situations where you don't have many data samples. Okay, so let's look at DDF now. This is our new data frame. Then we select the attribute and target variables. I mean, specify the input and the targets. Then now we split our data into train and test. Then we scale our data. Then now we just build random forest. So now to do that, you call random forest regressor, pass the number of estimators. By default, in fact, not by default, you cannot even change. I don't think you can change the base estimator of a random forest. You cannot change the base estimator, right? Let me see. So anyways, we call random forest and we put the number of estimators to be 200. That means we want 200 decision trees, and then we fit and we use the fitted model to predict on the x-text, and now we find the root mean square. Now look at this. The root mean square is 385. 385 compared to the one we have here, 530. You know, root mean square has to be as low as possible. So you can see that this random forest perform better than the single decision tree we have here, okay, for the same problem and the same data. So this changing of model from single model to ensemble model performs better. So that's just a confirmation, right? Now let's look at it again, another techniques to ensemble model. Remember I told you that two basic techniques for ensemble model is averaging and then boosting. We look at averaging with bootstrap aggregator, which is bagging. Now for the boosting, we want to look at Titanic, right? We want to do like boosting techniques. There are so many boosting models, right? You can have ADA boost, you have gradient boost, you can have which other ones can we boost? I think those are the popular ADA boost, gradient boost. Here we are going to use, I think, ADA boost or gradient boost. I don't know. So well, let's read our data set. Titanic. So what we want to do is we want to build this same data set, this same model problem, Titanic model that we use bagging. We want to use boosting for it. Okay. So let's check. We know there's no null value, but let's check. Then the same thing we did. We just define the input and the output. We split our data. We transform our data. Now we use gradient boosting classifier now. So here we just call the gradient boosting classifier, right? The default, by default, let me see. Gradient. Okay. We just call the gradient boosting classifier here, and we fit it on our training and our data set, our training data set, and we use it to predict on the X text, and we find the score. Okay. So let's see. Now this is 0.89. I mean 0.8, 0.8 for the gradient boosting. Let's look at it. Compare with what we have for the Titanic. The score for the Titanic, I mean for the bagging rather. For the bagging is 0.75. But for this boosting is 0.8. Well, you see guys, I'm just showing you some of the very core concept of machine learning, which is that one, a single model performs better than single model, and two, for a single model, boosting method, tends to perform better than bagging method. It is bagging here is 0.75, boosting here is 0.8. Now the question is why? Why do we have better performance with bagging model than boosting? I mean with boosting model than bagging. Why does bagging model perform better than, why does boosting model perform better than bagging model? Okay. Let me show you. Well, one thing is you can say maybe the parameter or something, but there is another technique, another intuition behind it. I think you guys you understood the bagging approach. Bagging is basically doing random sampling of some subset of the data and then now finding the average. Now, how does that different from boosting? You see, for boosting, I'm going to use red line now. For boosting, it's still going through the same approach as bagging. Boosting is using similar approach as bagging, but with a very simple but effective modification and important modification. Remember bagging, again, we took random samples of our data and fit it on different machine learning models. In this case, we use 5 decision trees here. And then we just took different samples, sample with replacement, then took another sample with replacement to another random. The point here is we took random, I want to use black for bagging. We took random for bagging, BA, we took random sample with replacement. It can be with replacement or without replacement, but the point is they are random samples. Anyway, now look at boosting. This is what boosting is doing. You see, boosting is also going to take random samples R1 in the first instance with, let's say, DT1, just as we have with bagging. So we have random sample R1 with DT1. Now, let's say for the random sample of the first random sample is from index 0 to, we have 1, 2, 3, 4, 5, 6, 7. Let's say 7 samples out of all these 713 samples. It took 8 samples now. This is 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay. For the first decision tree 1. After building the first decision tree 1, we are going to have our model, and we can now use our X, right, on our model to get our Y predict. We have our Y predict. After we have obtained our Y predict, for each of these, for each of these training, we have Y predict, right? We have Y test predict for this. We have Y test predict for this, Y test predict for this, right there. So basically what we are doing is that we are building the first model and we are using that first model to test our model. Now, what will happen, what boosting is doing is that it is now taking note which of these samples, this is where the modification for boosting comes in. It is taking note which of these samples give the wrong prediction, or which of these samples give poor performance on the prediction or on the testing. So it's now giving it weight. We have weight for each of the samples used here. Let's say the first one, 0 index, it predicted poorly. It has the wrong prediction. So it's going to give it a weight of 1. The second one, let's say it predicts perfectly. That means our model has learned from it. So the weight is 0. The second, this third one, let's say another one predicts very close but not too close. I'll give that one 0.5. Then the same way, just assign weight based on the prediction. What is now the use of this weight? It is now this weight that is the modification in the next, remember this is our DT1, and we want to build 5 DT. Then the next DT, right, DT2, right? Remember, it's still the same approach as the bagging. It's still taking random samples. But the contrary to bagging, that is just going to put the first sample back and take another random sample. Boosting is going to put all the sample back also, but it's now going to consider the weight of each of the sample in the next. It's going to consider the weight of each of these data points, right, for the next sample. What it means is that for the next sample, it's going to be random also as well. But then the ones that are predicted poorly will always be included in the next training for the next model, right? So this one that has 1 now, this one that has 0.5, this one that has 1, they will always be included because they have weight of high weight. Why are they included? Because we understand from our previous model that they are predicted poorly. That means they have not learned, the model has not learned from them. So we need to train the model on that specific data samples that predicted poorly. So what that one is doing is that it is sequentially boosting the learning of your model on your data set, right? So reduce the bias on your data set by in making sure that the samples that are not predicted very well in the first instance or in the previous instance are used for the training of the next instance, not just the samples, in addition to some other ones that have not been samples also will be taken also, right? But then definitely the ones that are predicted poorly will be included here in the samples. So this is it. That is why boosting performs better than bagging, because it considers the performance of the samples, or it considers how well your model has learned from the sample in the next training. Okay, so guys, this is the intuition behind bagging and boosting. So then the last one is for you guys to work on yourself, like maybe just for you to try and explore. So you want to use boosting for regression problem, and then you are using it for the advertisement data set that you have with you. So this is what we have for this lab. Just as a summary, we look at bagging for Titanic for classification problem using Titanic data set. Then we move to random forest for regression problem using ETA's dataset. And lastly, we look at boosting model for classification problem using titanic dataset. And we compare the two classification tasks, the first one on bagging and the second on boosting, and we realize that boosting performs better than bagging. But generally, ensemble model performs better than single model. Okay, so this is what we have done for this lab, and then we have come to the end of the lab. Except if you guys have questions for me, I'm going to take the question, and then we can then call it a day. Any questions from you guys?
So actually, for the first one, the titanic data set, can you explain again why do we need to get the range of that parameter?
Okay, thank you. So if I get your question right, you want me to explain why we do this part, right? This parameter range, right?
Yes, sir.
Exactly. Okay, good. You see, this is how I'm going to explain. This is called validation. Validation is what we call model selection. It's actually inside it's actually a broad topic. It's a broad topic inside model selection. Why do we call model selection? Is because I told you that now we decided that we want to use where is it? We decided that we want to use bagging here, right? Bagging for classification. Now, when we want to use bagging for classification, let's say I don't want to do this part of parameter range and all of that. I can do trial and error to select the parameters. I want you to understand the terminologies. Model, we have parameters. For each models, they have their parameters. Like for let me say for KNN now, where is my this thing? Like for support vector machine, I think for support vector machine, one of the parameter is kernel, right? And for kernel, we can use, and we did this, we use RBF, right? And also we can use, or we can use linear kernel. You can't use these two. You have to use RBF or use linear. This is the parameter kernel. These are the parameter values, right? Now, what we want to do in model selection or here is we want to find out, okay, by trial and error, you can use this one in the first place and see the performance, and then use this one in another instance and see the performance. But that one is going to take your time if you want to check for many parameters. That's why for bagging classifier, is an ensemble model. If I say bagging classifier, now I want to build my bagging. My base estimator, I want it to be decision tree. So I'm just going to put decision tree or something, or let me just say DTC, decision tree. Now, the number of estimators, this is where the parameter range comes in. The number of estimators here by default is 10. And what that means is that I'm using 10 decision trees. But that is by default. But I can change it to maybe 50 or something. But the question is that, how do you know that 10 is the best to get the best performance? Because there are points that if you use less number of Excimators, in another word, if you use small number of decision trees, your model is not going to give you good performance. And if you use too many decision trees, there are two problems with that. The first problem is the computation cost. If you use 1,000 decision trees, it might take your model 24 hours or a day to complete. And another thing is there can be overfitting, right? So the question is, what is the best parameter for me to use what is the best parameter values for me to use in my model building. So I can say n estimators now. Now listen, I want to say number of estimators, right, equals, by default is 10. Well, I say, okay, maybe I'll try 20 or 30 or 40 or 50. I can try as many as possible, right? And then now, this is where we now use this validation curve. You see, validation curve is used to, that's why we say, okay, look at here, create range of values for parameter. We now say, okay, let's say I want to check between 1 and 250 to determine the best parameter for, to determine the best value for this number of Excimators. So 1 to 250, step of 5. So it's 1, 6, 11, 16, 21, up to 246, right? Okay. Then now, when I'm using validation curve, right, what I can use is I just call the validation curve. I'm going to pass my model, which is a bagging classifier. And now I'm going to pass my data, X twin and Y twin. Then I'm going to pass the parameter that I want to find the best value for, which is the number of estimator in this case now. So this one is saying that for the number of estimators, I want to find which is the best parameter within this parameter range. So instead of calling parameter range here, I can just call this, what's it called? I can just put this value here, Control C, and then put this one. I can put it like this. That parameter, that what I'm saying is that for the number of estimator parameter, can you check for this range and now give me the scoring accuracy? So after I do, the return from this is that it's going to give me the training and the testing scores. Remember, training score is the one on training, testing score is the one on testing. So now, eventually, I can now, this is just like finding the mean and then now plotting it. I plot the, what's it called? The two curves, the training scores and the testing score. So the main point or the main aim is for me to determine the best parameter here. I can now say, okay, from here, I think the test, the validation now has very high performance here, and also for the training, it also has high performance. So I want to determine the best performance, the best values that give high performance on testing and high performance on training. So when I have decided that, okay, I think my value, the number, you can see the number of trees. I think my number of trees are around maybe 50 something here. I can now say, now I will now build my what's it called, my bagging classifier now. My bagging classifier, I'll use DTC, I'll use number of Excimator. Now for the number of Excimator, I can now be certain that yes, now I've decided that the best is this value 50, maybe 60 or something. Just say number of Excimator is 60. Right? So I can now do my do this thing again, do this model building where I use where is the model building? Where I use 100 in the first instance. I can now use 60 here because I realize that I think 60 is better than 100 here, right? Because you see 100 here is this, but 60 is somewhere around here, and maybe 80 or something. So this is the use of the validation curve and the parameter range. It's just for you to determine the best parameter values and also used to determine the best model. I hope that answers your question.
Yes. Thank you, sir.
Okay, good. So any other question from any other person? Okay.
Sir, can
yes.
I ask about questions from the other chapters? from the other lab.
Yeah, please.
So because we are going to have a quiz today on SVD and PCA, but after reading the notes, we are still confused between SVD and PCA. Like what are the difference and what are the application of SVD and PCA?
Okay. You see, the point is to be sincere with you. I actually don't use. There are dimension reduction approaches, right? But trust me, I also don't use them. I don't use them also. I don't use them at all. But I understand that their use, the application is that, in situation where you have many features, especially, you see that dimension reduction techniques is most used in deep learning when you have many pixels and channels of images, and your data is getting so overwhelmed with data samples and features. So you want to take away some features. So to do that, the PCA, principal component analysis, is used to transform your features into maybe 3 components. So that feature transformation is about, just combining multiple components or features into one component. Then another component into one component, depending on the number of components you specify. But the thing is that I really don't, I have not been using them in my machine learning task, because in most cases, it's not like I have 200 features that I want to use. Most of the time, I've been working on very little number of features. So I don't really feel the need to transform or to reduce the dimension of my machine learning something. So basically, just to understand that it's used for PCA, and I mean the PCA and the SVD, they are used for dimension reductions. If there is any problem that requires that you do dimension reduction, then maybe you might want to explore it more. But I also have very limited knowledge about them. I don't know much about them also, but I know that this is what they are used for. Okay, I'm sorry.
All right, it's okay, sir. Thank
Okay,
you.
you're welcome. Okay, so no question again. Mr. Naim, are you there?
Yes.
Okay, so you have the class.
Okay. So no more question, students? If not, then we can dismiss our class. Then next week will be our last lab session. So make sure everybody is there next week for lab 10.